When we look at several popular neural networks that are basically composite neural networks that are used as components of other networks. Usually we won't build a network from scratch, but rather reuse existing components. Okay, so these are reusable units, and they are a composite. They are not. They consist of more than one small unit, and we'll discuss several popular ones. There are many. This is, of course, not an exhaustive survey. Okay, but for example, if you look at the famous transformer, which is used for text, then you can see that it is defined by a combination of these blocks, each being a neural network of its own, DNN of its own. So we see here the multi-attention and the feed forward, and these are basic units, the linear and the softmax. Okay, so we're going to look at feed-forward networks, and specifically the MLPs, and then the attention mechanism, which is one of the most important neural networks, okay, or components of neural networks. So, starting with feed-forward neural networks, well, these stand for a very general family, the family of neural networks where you can represent or conceptualize as a flow of information in one direction from the input through the intermediate layers. No parameters are shared until you get to the output. Okay, this is very general. Okay, so it will be defined by layers, maybe one, maybe a few of units. Okay, now the connections between one layer and another can be either fully connected um, neural network, which means that every input connects to every output, or selective, like in convolutional networks, where subsets of the input layer connect to subsets of the output layers by some rules. Okay. Now, the contrast of feed-forward networks are the recurrent networks, like RNNs, LSTM, uh, where the information can be, again, conceptualized as at some point going backward, okay, applying again the component of the network, which is something that is useful for processing long text, for example. And you're accumulating information and memory along this process. You do not want the text to go through one fixed model, okay, because you want to apply it again and again. Okay, now I'll just say that in practice, when you see the term FFN, like we saw previously in the transformer, unless it is given explicitly and it is something special, it refers to a simple composition of layers, like linear followed by some activation unit, not much sophistication. Okay, this is a visualization, feed-forward network. We start with the input, okay, going all the way to the output. So this is fully connected. Everything is connected to everything between the layers. And this represents a recurrent neural network where the input layer is fed by the first layer, then the next layer in this figure, right? And then this output is again processed by the green hidden layer. And in the end, you get your output. Now you might say, well, how long do you run it? It may be defined by the input. It may be some predefined number, but it's not the same as duplicating the same network again and again, even if it's a fixed number of occurrences, because when you learn it, you update the same parameters. Okay, so we have the parameter sharing in this mechanism. Okay, we are not going to discuss recurrent networks in this course, just for our knowledge, contrasting with FFNs. Okay, now the most important example of an FFN is the MLP, uh, multi-layer perceptron. Okay, MLP is a sequence of fully connected layers, very simple, linear and activation units, followed by the output. Okay, now, but this is a family of components. So different MLPs can have different layers or number of the layers. The activation unit can be different. It's usually the same activation unit applied again and again. Um, the width, the dimensions that you're using there, these might be different, of course. And the way you combine things in the output layer, in the decision layer. Okay, so we'll see an MLP for multi-class classification with C classes. The input is a vector of length n, okay, and the output is a vector of length c. C is a probability distribution over C classes. Okay, and you can guess which unit is going to produce this probability distribution. Okay, now we assume that there's an activation function phi, and this can be any one of the functions like that we've seen before, like ReLU. Okay, so this is the definition, very simple. The first layer H0 is X. The next layer H1 is simply a linear transformation of the previous layer, followed by the activation. Same for H2, same for HL. Okay. Again, I remind you that different AIs and BIs use different parameters, no parameter sharing. In the end, we get the probability distribution using softmax. Okay, so why the output is a softmax of the last layer, HL. And so we need to make sure that the dimensions of these linear transformations match a dimension C, because then we apply softmax on C dimensions and get as a result a distribution over C elements. Okay, this is an example, okay, for disease diagnosis. Okay, and you can see the features basically getting in as the input layer, fully connected to the next layer, then the final decision is made here to decide on the terms to predict.